Well, everyone, welcome to Maths 2504. You guys have just finished your big homework. Who here thought the big homework went well? Anyone? Who here thought it was like a little bit challenging or not quite as good as you hoped? Yeah. Is there any particular reason or any particular bits or bobs people want to highlight that they just thought was a little bit tough or anything before we continue? You want to volunteer their experiences or? Yeah.
I think it was really long and
really
some
long.
of the questions were very clear.
Oh, you didn't know how to like answer the question, what the definition of success was for that question or something. Yeah, okay. Yeah.
And like as someone who hasn't done a lot of like proper programming,
Yeah.
I feel like it was a bit harder than I expected, like the very first assignment before. It's like
Yeah. So pretty tough for a programming newbie. Yeah.
Like something else first and that like a later like something else.
Yeah, I'm not Yoni, but the way Yoni explained it to me, the uni sort of cut back on the number of different small assessments we can give. So it's hard to give something a bit more graduated, but yeah, that's probably good feedback. Thank you. So as you know, we are here on August 28th. Tomorrow, I'm not lecturing. Tomorrow is the quiz. Okay. So as Yoni reminded you last week, when he was here with me, for that you'll log online at the allotted time, perform the quiz, and do your attestation at the end. Yeah. But today we're doing Unit 4, which let's just get that up here. Where's the Unit 4? Okay. Yes, question over here. All right. Sorry, I couldn't actually hear. Say again. Well, I think you can finish when you're finished. No, so if we recall what Yoni said last week, and I'm not the course coordinator, so nothing I say is actually valid. But Yoni said last week, just sign on at the start and say hi. And then you can just go away and you as long as you submit in the time and do the honesty attestation thing at the end. Yeah. Okay. So as I said, we got Unit 4 here. I'm going to go to 2 hours of this today and 1 hour of the next week's lecture before we actually move on to the next unit, computer algebra systems, which will be in Project 1. So the purpose of Unit 4 here is to give you all that kind of background knowledge, like especially if you're not completely new to programming, explaining all these things you're seeing in Julia. So if you're not very new to programming, this set 2 lectures, or the 2 hours today is going to be a bit of a blessing and a bit of a curse, because I'm going to explain pretty thoroughly all the things you see in Julia. But if everything's completely new to you, you might find that a bit overwhelming. You might want to go rewatch it. Yeah. But the concept is, again, well, 2 things. One thing is really, Julia is about giving you this ability to execute fast mathematical code and to write it easily and to not get bogged down in complexity as you're writing bigger and bigger programs, right? So we're learning how to use those tools and what those tools are to help us do those things. But we're also going to give you all the tools and understanding you need to do Project 1, Project 2, and Project 3, which are going to be where you have to write programs yourselves, okay? So you've sort of seen a lot of programs, you've done homework 1, you've about to do the quiz. So you sort of have some understanding of how Julia works, but we're trying to go in a bit deeper. But as Yoni mentioned, Unit 4 is not directly accessible. You consider this background material. If there's aspects of this which are hard, go over your head, it probably won't matter, right? Just there might be bits here which you know, you find sort of interesting, or there are bits which are maybe going a little bit far, but you know, just try and follow along and have some fun. And please ask me questions, because the purpose here is really just to explain stuff. Okay. So if you get bogged down, just interrupt. It's fine. So last time I gave a little bit of a history and just spoke about the different types in Julia. So there were primitive types, structs, tuples, and arrays and strings, basically, and that's it, right? So there's not too many types. Today, we're going to start on this idea of that just defines the data that you can have in Julia. What are the operations you can do with that Julia data? What operation, what logic can you do? So let's just talk about the syntax for expressing logic, and then we'll go into functions, multiple dispatch and stuff. And then next Monday, we'll actually get into hands-on experience. We'll type in different programs, create our own types and that kind of thing, create our own functions on those types. And that's the kind of stuff, that hands-on stuff that we'll have the background for today and we'll do on Monday, next Monday, is what's really going to help with things like Project One, where you'll be creating your own types and using user-defined types. Okay, so we've covered all the possible values, so let's look at the logic. One thing, and I mentioned this last time, is that everything that's valid syntax in Julia produces a value, right? That value might be the value nothing. Remember, there's that special value nothing, but it always produces a value. And all values have a type, right? They have a concrete type. And you can ask Julia, what does it think the type of an expression might be? Okay, so there's this macro, and I'll mention macros again in a little bit. But there's this macro which will help you determine the output type of a piece of code. Okay, so this function, this 1 + 1 is actually syntax sugar for the plus function on 1 and 1. Okay, right? And that just dispatches to this base.addIn. So there's this built-in thing in Julia that helps it know how to add numbers on your CPU, right? And different CPUs will have different instructions underneath. And on this last line of this output, you see what the output type is. Okay. So when you add two int64s, you get an int64 back. Okay. So Julia hasn't really used the value 1 and 1 here to figure this out. It's actually just used the type of 1 and the type of 1. So it's not doing value propagation here. It's really propagating types forward in an abstract sense. Now, sometimes it can get confused, and we'll talk about that in a minute. Why would it get confused? We've seen in Julia if statements, right? So if statements are also expressions. Well, I shouldn't call them statements, they're expressions. So there's a sort of a true block and a false block, or an if and else block, if you'd like. And you get one expression or the other expression evaluated and returned to you depending on the predicate. So this thing here, I usually call that the predicate. It's usually some expression that has to evaluate to a bool, otherwise you get an error. If you sort of run this with the number 42, you get 42 as even. If you do it with 43, you'll get 42 as odd. Okay. And like Julia, in like a lot of languages you might have seen in C or JavaScript, there's these ternary operators. So there's this operation here. So if I highlight all that, there's actually 3 components here. There's this first bit here, the predicate, and then there's the sort of true expression, and then the false expression. So the ternary operator is actually 2 operators. It's a question mark and a colon. Okay. But this is really, it's just syntax sugar for that. There's nothing at all different about the ternary. It's exactly the same thing. The very first thing the Julia compile does once it's read your code is do a transformation like this and a few other transformations. So it's just syntax sugar. It just makes the code a little bit sweeter to write and a little bit sweeter to read, but it doesn't really do anything else. Okay. Just like operators in Julia are syntax sugar for function calls. And plus itself, and I should get this up. I should have had this up already. Plus itself is a function. You know, you can go plus. You've probably seen this with Paul and everything. All right. Sorry, my keyboards. Yeah. So yeah, so the question is, why are there 207 methods? And I was actually going to get to this today, so we can talk about this now. So the plus operator is overloaded with a whole bunch of things. Okay, so Julia has int64s, it has int32s, it has floating point numbers, it has rationals, it has complex numbers, you can add matrices and vectors, right? Here we got like, you can add a number of months to a date. Right, so you can say today's date's August 28, you know, in 1 month from now, it's September 28. And there's all sorts of different things in here. If I went and imported a bunch more libraries, they would overload plus for their own types potentially. And there might be 300 methods in plus then, okay? The plus is a very extreme case, right? If we take something like the sine function, it has only 14 methods, right? If I take something like the show function, well, a lot of types have a show method. Shows like the text it prints when you get it at the terminal to show you what it is, okay? But, you know, a lot of things, you know, don't really have many methods at all. But that's a good question. So let's have a look at this ternary thing again, or an if-else statement. Imagine the true block returned true and the false block returned a string false. Maybe this is even just a typo, right? But imagine it did that. What's the kind of output type of that function? Right? Any punters? Yeah, it could be a bool or it could be a string, right? So if it's an even number, you'll get a Boolean, and if it's an odd number, you get false. And if you ask Julia what it thinks, just again focus on that very last line. It thinks it's this union of bool and string. So just let me grab this. Last week I had this little picture of sets of types, right? So we have the bool type, which is like a set with true and false in it. It just has 2 dots in it, right? And then we have another set of strings. And that's sort of an unbounded set because, you know, strings can have arbitrary lengths, so there's lots of things in there. And the union type is an abstract type. So there's no value of type union, right? But all it's saying is if I take a union of those 2 sets like that, then that's the union bool string type, okay? So that contains all the bools, so true and false, and any possible string. Okay. So that's our first abstract type. And kind of coincidentally, I suppose, like there were 3 concrete types we were going to look at, there's 3 abstract types in Julia, really. Okay. So another thing you've probably seen a fair bit in Julia is this shortcutting logic. So let's just take a step back. What's the shortcutting of? So it's a shortcut for Boolean arithmetic and or. It's a logical conjunction, logical disjunction, whatever you want to call that. And you know, you can kind of, you know, false and false is false, true and true is true. And you can kind of have this truth table, right? I should put a semicolon there. And or, so or is true if either of them are true, whereas and is only true when they're both true. So there's this, what can happen sometimes is the thing on the right, let's say you do X and Y, let's say Y was very expensive to compute, okay? Well, what's going to happen when you type X and Y? It's going to compute X, it's going to go away and compute Y, it's going to wait till that's finished, then it's going to do the AND, okay? But if you already know X is false, you could skip all that hard work of computing Y. So that's what the shortcut means. It's to accelerate your code. It's also used if Y could be any expression. It might print something to the screen. It might throw an error. It might launch the nuclear bombs. You know, there are certain things you could put in there which you don't want to happen if X is false. Okay. So the way that's implemented again is with syntax sugar. It's really just equivalent to this expression. Okay. So if X is true, then compute Y. If it's not, just return false eagerly, sort of as a shortcut. And the one sort of consequence of that, which happens in Julia, is that the thing on the right, the Y, doesn't actually have to be a Boolean at all. It could be an expression. This expression returns nothing, but it could return some other number or object. Or it could throw an error, as I said. So often you'll see people write things like this. I just want to put this here because I don't want to confuse you or scare you, right? It's really just a shorthand for this. I think when you're learning programming languages first time, having 100 different ways of writing the same thing can be a bit of a handicap. But when you're writing day in and day out, some people prefer to write less code, I suppose. And if they're used to the syntax, it doesn't bother them. Now, if I had this expression here, x less than 0 and print that, what do you think that would do? Any ideas of what this expression would do? Here, I'll take it to the terminal. What's going to happen when I press enter? Does anyone have any thoughts or guesses? Or oh, it is going to ask me what x is. That's correct. So let's press that. I didn't define x. Apologies. So let's take our trusty number 42 for x. Excellent. And now if I run that, what do you think it will do this time? Okay. So I'm going to press enter. So what's it done? It's done a couple of things. First, it's evaluated the left-hand side and it's evaluated the right-hand side. The right-hand side has printed x is negative to the screen, even though x is a positive number, right? And then it's trying to go, I think it's false and nothing. And it's saying, oh, there's no methods for and, for Boolean and nothing, okay? And we can look at all the methods for and, right? There should be hopefully a few less than, there's only 17 methods, but none of them involve nothing, right? The nothing type. Okay. So there's this double or one, which is short circuit using or. It's used the same way, except for it's more like, if you know x is true, you don't have to evaluate y, right? Because true and anything is true. Yes.
If it says that it's 100% improvement, I don't think it works. Second statement is like assignment. You try to do somebody else.
So in Julia, yeah, the question is it the same if it's a, so if I can go like true and if I can do something like this in Julia, this is quite weird. Okay. I can do this in Julia. Or I could do a double and, right? Either way. And what it's going to do is it'll actually define y for me, right? So even in Julia, when I say everything's expression, even assigning variables is expression, and it returns the right-hand side, the thing you're assigning to. If you notice here with the and, it's actually defined for integers. So often this is probably a product or C or something. You can and together any kind of type, and so long as it's not 0, it'll give you true. Assignment doesn't return true, it's actually return 12. So I can go like true and 12. Let's see what this does actually. Okay. So I think if I do 1, so 1 is equivalent to the Boolean true and 0 is equivalent to Boolean false. Okay. And I think it's just sort of making that conversion under the hood for me. So maybe that's a bit of a tricky case, but it's a bit of a quite a conceptual error to put those types in. But yes, okay.
What's the type of y?
Yeah, okay. So if I go y equals 12, yeah, what does it print out? 12. So I can go like z equals y equals 12, right? And z is also 12. So it just forwards the right-hand side of that assignment to as the answer, right? Because it really doesn't matter. You've set y equals 12. You could return y, which would be 12, or you could return the right-hand side, which is 12.
So one is the only number that is true.
Apparently, I don't know about this. I haven't really, but this is definitely true. These are definitely correct.
So put it there to
Ah, yeah. So if I put 13 instead of 12, interesting. So it's apparently it's modular 2 arithmetic. Okay, so odd numbers are truish, false numbers are falsish. Okay, we all learn everything, something every day. So that was fun. Thank you. Blocks of code. In Julia, blocks of code, you can create a block of code, but they'll turn up naturally in if statements and functions and things. But if for some reason you want to create a block of code, you can just begin one with a begin. Okay. And blocks of code, what they return is the last line of the block of code. Okay. So usually you're doing some computations or you're creating some side effects in the middle. But here we just have 1, 2, and 3. And so the 1 and 2 here are kind of impotent. They don't do anything, right? It would be just the same code if I deleted the 1 and 2 lines there. And it just returns the 3. But these could be print lines or throw errors or something else that's sort of effectful. But you'll see blocks of code just appear naturally, like inside of functions. Starts a block of code, and at the end of the block, you've got to put end. While loop is a block of code. At the end, you put end. You know, if and else create blocks of codes, which you put end afterwards. Okay. And so just conventionally, we add these spaces to indent it, so it's very clear where the blocks start and end. But the compiler doesn't require that. You could write that all with no spaces beginning the lines. It will still accept the code. But for humans, we add these spaces because it makes it a lot clearer when which piece of code's running. Otherwise, you've got to really read it like a computer and sort of compute it in your head. And it's a bit much. Okay. So like this particular code, it sets x equals to 0 and prints out what's even and odd. And then it adds 1 to it and then loops around until it reaches 10 and then returns x itself. Okay. And so it's printed all this to the terminal and then returned the number 10. Just note that, so the return statement will leave a block kind of early, a function early. I could have just not put that return there. And the function would have returned x anyway because it's at the end. And it would just take whatever value is at the end of the block. The while blocks and the for loops and while loops return nothing by default. Okay, that's just the way they work. But also empty blocks of code return nothing. So if I go begin, end like that, it just returns nothing. Okay, so I can like put this here, and I can sort of say, okay, what was that answer? That answer would have been like just, I can't see it here, right? So one thing you can do in Julia is called the dump function, and that will make sure it prints out exactly what it is. So it's of type nothing with value nothing. That's how you read that. Yep. Similarly, you wouldn't ever really do that, but you might have like an if statement where you don't really care about having an else branch sometimes, right? So if this, so that's kind of equivalent to having an else branch, which is an empty block, right? Rather than the absence of else, you could just say it's an empty else block. And an empty block is equivalent to nothing. So this bit of code with just the if, sometimes it will return nothing. Okay, and this is where you can get those union types back again, right? Pretty easily. If I assign that to a variable, it could be an integer, it could be a nothing. All right. How are we going for time? Good. So if we, yeah, the nothing type. So because Julia returns nothing for empty blocks and stuff, it's also the type we tend to use in our code when we have functions which do something, but they don't need to return anything. So just by convention, a function like printline would also return nothing. Because the purpose of printline is to do something to your terminal. It doesn't affect any variables or create any values for you to interfere with. But you might have programs which read to databases or do different things. But when you're doing things, you're not really producing values, you're just doing things. So has anyone here used C? What do they call this in C when you have a function which doesn't return a value? Do you remember? The void. Has anyone ever used void in C? So void is this sort of concept that you have these You have functions which return values and functions which are void. They have no return statements. Here we implicitly have return nothing if there's nothing else to return. Sort of makes it simpler in some ways and more complex in others, I suppose. And the way it makes it simpler is everything's this expression which returns a value, which is kind of nice. It's really nice for copying and pasting code and understanding what's going on with the syntax and being really flexible. But it also means what we can do is we can take an expression and apply a macro to it. So in Julia, I said Julia codes can be written as an expression. So for example, let's say I take this thing. Let's have a look what I mean by that, just real quick. I don't even need to copy that, that's so short. So I can like take x plus 1 and figure out what the expression for that is, and I'll dump that. And it's this object called expression, okay? And I could do something like this. I could go like expr plus x1, and I would end up with exactly the same thing. I've done that wrong. Maybe I need to do that or something. But you can construct those things. And this is what you do in a macro. So a macro will kind of like read this code on the right and then transform it. And the way it's transformed in the show one is it calculates the thing you want. Here on the right, and then puts some text here which looks like the expression you gave it, okay? So it might get the spacing or something a bit different, but that's the kind of transformation that macro writes. So if I go, so we have x, don't we? And if I go show x plus 1, we get x plus 1 equals 43, right? It's fine. But this is really cool. You can do all sorts of interesting code transformations and doing metaprogramming. So you build programs that build programs. But in Julia, it's really cool because you can use multiple dispatch to make programs to build programs. What multiple dispatch does is it lets you define all these data types and all these functions, and then put it together like Lego blocks when you start calling the code. So the really nice thing here is someone over here can write some package with some types and some functions, and someone over here, well, let's say some types, right? Someone over here can write a package with some functions. I can import them both and put them together, and these two people have never spoken to each other, okay? So the Julia code's composable, and you can kind of build programs and build, you know, sort of code, paths of code that no one anticipated, the original authors never anticipated, just by piecing everything together like Lego blocks. All right, so that's sort of the logic, that kind of some of the expressions. So I'll go into how we actually create functions. So functions are very core to Julia, functions and methods. One problem is they're so core to Julia, they weren't satisfied with just one way to write a function or create a function. There are many, many ways of creating a function in Julia. So the one which is probably the most clearest is it just starts with function, has a name, has some arguments, and then some logic in the middle, right? But sometimes that can be quite long-winded, especially for something as short as this. So there's a shorthand form which looks like that, which you might have seen. But this is syntax sugar, right? These two things are 100% equivalent. There's nothing different. Well, one's got F1, one's got F2. But other than that. And then there's this one. So this thing here is an expression, okay? That expression returns an anonymous function. So it's a function, there's no F3 there. That function is constructed at that point in time, okay? And then you're assigning that to a variable F3. And I've just put const here because it helps the compiler realize, like, figure out what to do with that function at compile time, as opposed to trying to figure it out slowly at runtime. But this in itself is its own little arrow function, and it creates an anonymous function, so with no name. But when I'm talking about anonymous and not anonymous, this has also nothing to do with the syntax. I could create an anonymous function here in long form. So the arrow function also has like a long form, right? So here it looks weird because it's just brackets, right? And there's nothing there. But if you see something like that, it's creating an anonymous function, and then we're binding it to that variable. Oh, that's my fault. Those error messages. I created some F's further up. Silly me. Okay, we got F1 and F2. So that was these two definitions. They were the same definitions, but they actually have their own types. So every time I create a function like sine or cos or plus, Julia will create a new type just for that function, and that type will hold those methods that you attach to the function, right? All the logic, all the different ways you can use that function. And those 5 types are distinct, okay? So the type of F1 is not the same as type of F2, okay? But these types are like that nothing type. It's like a struct with nothing in it, right? It has 0 bytes, but you can attach methods to it, okay? So a function is very much like a struct by default with just nothing in it. Like we saw before, oh, this is fascinating. I've been reusing the variable F1. So we can use this method sting to figure out what's inside of it or what's attached to it. And so we've got this definition, which I wrote here. And that's this second one. And somewhere earlier up on the page, I defined F1 as well on a different line. And it didn't have any inputs. So, but things can have any number of methods, including 0. So like nothing, it's just a value. It doesn't have any methods. But neither does the number 3. The number 3 doesn't have any methods, right? But we can change that. Julia is very flexible. You can do whatever you want. Every single object or every single concrete type or abstract type, you can put methods on. So this is the short form of creating a function, except here, instead of calling it by its name, we're kind of saying, okay, if the function is of type bool, we'll call that x for the moment. It might have data in it, right? So x. And we call it with no arguments, then I want to return this string, okay? So, and there's a short form and long form, they're equivalent, right? That's kind of crazy. You're not going to probably do this at all. But operator overloading in Julia, you can also overload the function call operator, so to speak, if you've seen that before in other languages. If the type is singleton, so like sine and cos and all those functions which have 0 bytes attached to them, you don't actually need to do this crazy colon type thing. You can just use the singleton value and Julia will figure it out for you. And so this is actually, there's a fair bit of complexity in like f of x equals x plus 1, right? It's actually, you know, creating this type for f and then the singleton value f, and then you're doing this thing to it. Now, why do we keep talking about functions? Is it? Oh yes, go ahead. Sorry.
So like when you need that it's expressions by default, I would think that it's like gonna do and you're gonna like mess with that.
So by default, I can't like call functions. Like objects of type bool are not callable. Well, Julia, I disagree. Objects of type bool are totally callable. So if I run that now, it will do that for you, okay? So, and you can do crazy, and Julia is very dynamic. So like one thing, I'll just open a new terminal, okay? So I can actually change something like, I can go like base dot, I think the syntax is like this, right? Of say, x integer and y integer, right? And I think this will work. I'm not sure if this will work. This used to crash Julia. They might have fixed it, but I can overload. Okay. So if you notice, it's just flashing and not doing anything. So what I've done here is I actually created an infinite loop somewhere. It's probably like trying to add a counter in a loop and it's just getting 0 back every time and it never reaches the upper part. But you can kind of quite easily make Julia do sort of stupid, crazy things. And I just want to kind of like kill this. I'll probably have to restart my computer, who knows? But yeah, but basically you can attach at any point in time new methods to things and override the existing methods, right? Yes. Yeah, so is there a way to clear your workspace? Your workspace is this module main. So by default, you're kind of living in this module called main. Okay. And I think there is a method. I don't know how to find it. There's a function you can call that will basically recreate a new main for you. So it's fresh. But if you've overwritten like the compiler or something like I just did, you kind of cooked. But yeah. Well, rather, yeah. So constants kind of like it. Julia likes constants to say constant, so it doesn't like you messing with that. But what you can do is you can like take that whole module main, throw it in the bin, and create a new module main with nothing in it, and then find constants in that. Yeah. Yes.
So the syntax for writing types method.
Yeah.
Seems like it should be what I would expect with this syntax, like having a type anonymous function.
So where did I define that? That's this one.
Yeah.
A typed anonymous function. Oh, well.
Oh, actually,
no. So with the anonymous function, this whole highlighted bit would just be deleted, wouldn't be there at all.
Okay.
Yeah. Yeah. So it's not that we've really given a name, but it's we've found a type to attach it to, basically. So that when I type methods, it looks up the method table attached to type. Yes?
Where it says anything can be made call.
Yeah. Yeah, well, we can make, again, something like that, right? And then I can go like, whee! Oh, no, that didn't work. My bad. What just happened? Oh, we're going to have trouble. We're going to have real trouble. This is just pretend that never happened. This will work, I swear. So there's a syntax sugar in Julia where you can go like x, and you can go like 3x, and you can go like x equals 100, right? And then you go like 3x, and it's like 300. So juxtaposition in Julia is multiplication. And it got confused between trying to multiply 1 by the empty brackets, which is a tuple. So this thing is a thing. It's a tuple with nothing in it, right? And so it's getting confused. So all these little things is why I'm trying to get through lots of detail here. So like at least you've seen the most obvious weird stuff, right? Cool. Now, before I mentioned, I was talking about putting functions on Booleans and talking about by default functions have no data attached. Like, why would you want data attached to functions? And the answer is closures. So a closure is a function. It's just a function. But when you construct that function, you construct it with some extra data that it has in its context, right? So, and that data is sort of captured at construction time. And then when you call the function, you can use that data later on, okay? So while the function exists and hasn't been called, it has the data inside of it. And the way it does that is it just grabs things from the scope. So let's just have a look at this. This is actually quite a lot of syntax. So let's just step through it step by step. We're creating a function called adder. It's going to return a function which adds things. Okay, so that's why it's the adder function. It creates an adder. So let's say I want to create a function which takes an input and adds some number to it. And I want to tell you what that number is. And every time I call that function, I want to use the same number to add to it. So it could be like increment by 1. Okay. So let's say x is 1. What it's doing is it's returning a new function which adds 1 to x, adds 1 to its input, to y. Okay. So this is a nested closure. this thing I've highlighted here is the expression, and that expression refers to one of the inputs of the function, and it refers to something that lives outside the function. Now, normally when we write functions, we're referring to other things. We're referring to print line, and we're referring to the plus operator and all these different things. Most of the things that it's referring to are just constants, and on top of being constants, they're also like singletons, right? And the Julia compiler just says, okay, they're constants. We don't have to capture them inside this function. We can refer to them. We know what you're referring to, and that's not going to change. In this case, it doesn't know what x is. X isn't really defined until someone calls adder. So it has to kind of like defer that binding of x until someone calls adder. And then it creates this function where it knows what x is, which will add x to y. Is that confusing? I feel like if you've never seen closures before, this is just like, whoa, and why would you want to do this? Okay, and things like that. But that's the thing in Julia. Functions can return functions, right? Functions can accept functions as inputs and return them as outputs and stuff like that. So let's create add2, which is adder of 2. And then if we go add2 of 3, we go 3 plus 2 is 5. Okay? That's the way it works. Now, I just sort of said this adder thing, or add2, it must know its value of x. So its value of x is 2, right? So it's inside add2. It has to be stored there because someone else might call that with 163, right? And that version of adder will have to know the number 163. So that's stored inside there. And it's like a struct. It has fields with the names of the things it captured. They're just the variable names, right? And it has a size. So it has 8 bytes. That's an int64 inside there. It has 8 bytes of data. So if I want to send that function somewhere else, the computer actually has to like physically move those 8 bytes somewhere else. If you want to store it in an array, you have to put 8 bytes into that array. Well, they're constant things, right? So there's the stuff Julia can track for your compile time or the logic of the function. It keeps inside the compiler and reuses that every time you call the function. And then there's, okay, well, for this version of the function, there's an x. For that version of the function, there's x. And there might be 1,000 different versions of the same. Like, if you had a complicated program, you might have called this thing 1,000 times and stored them all in various places. And all those x's need to be kept somewhere. Whereas the rest of it can be stored once in memory with the code to execute. Yeah. But there is tons of metadata there. Like, when you start Julia, it takes like 100 megabytes of RAM to instantiate all those plus function methods and minus methods and print line methods. Okay, so the really fascinating thing, and this blew my mind the first time I learned about this, I think this was the approach C++ took way, way, way back in the day, but with Lambda functions. All this is just syntax sugar, okay? So this adder thing created this add2 thing. Now it has a type, right? So it has this weird type, so it's just created some random string. So the hope here is there's no other thing of this with this name, and it sort of does that by construction. It has a counter and stuff, and it never clashes. Right, and it has this type parameter, which means it's, in this case, when you've constructed it, it's captured an int64, that x is int64, right? And it also has a method attached to it. So that type has this method attached to it, which has this input y, has the data x, and then it combines them together when you call it, adds them. All right, and so the way you could do this is you could create this adder struct with x inside of it explicitly, attach a method to that type, which looks like this. You know, create the adder function, the lowercase adder function, which constructs one of these members of this struct, and then gives that, right? And if I did all that typing and I go add2 or 3, I get 5 again. So Julia can just sort of transform your code into, it can flatten out those nested functions to flat functions and put all the data, the captures it needs and deal with it that way. And that's the way it works. Bit crazy, but it's kind of cool. Now that, again, we're going way into the details here. Like none of this is accessible or something. I just sort of want to get you some feeling of, if you're kind of interested in how functions work. Type assertions. Okay, you might have seen this double colon things, especially on functions when you call this function accepts an integer on this kind of thing. So it actually means something. It's an expression in Julia. What it does is if the types match, if the value matches that type, it does nothing. It just returns the value. And if it doesn't match the type, it will throw an error, an exception. That's all it does, okay? So if I go 42 : string, it'll complain, type error. And this is called a type assertion, all right? Expected string got N64. All right? Now there are abstract types, like there's a super type of integers, which are number. And so 42 is a type of number. And that's true because integer is a subtype of number. And again, when I'm talking subtypes, think of these sets, they're subsets, right? And so this is a sort of predicate. It returns a Boolean, whether it's a subtype or not of the other. And there's also this type any. You've probably seen any by now. Any is like the type of everything. So every value is a type any. It's a super type of everything. Okay. And where they come in handy, as I said, is you can put the argument types on the function. This is useful for documenting your code. So when someone else reads your function, they're like, oh, if I want to call f, I need to use an integer. That's useful to know, right? That's handy. Because if you're writing with a team of other people, or you're writing your own code and you come back to it a month later, you could kind of forget, how do I use f? Why didn't I give it a better name? That kind of thing. But also in Julia, what we do is we tend to overload functions with lots of different methods and let Julia choose the method that's appropriate. Like we saw with plus, you can add integers, you can add floats, you can add different things. Here we could add different things on it. And Julia will let you call them with sort of different types. Okay. So in this last one, this is implicitly like : any. It's sort of like if x is any, then use this method. Okay. I'll talk more exactly about how the dispatch algorithm works later, but the way it works is that if you send it a value, it'll find the most specific method that matches and then use that. Oh, dispatch. We're talking about dispatch here. Yeah. So I'll just run through dispatch and then we'll take our break. Okay. So I keep talking about dispatch. So when you call a function, Julia has all these methods attached to the function. Maybe it has 0 methods, maybe it has 10 methods. Maybe it's like plus, it has 203 methods. It has to figure out which one to use, right? Because they might all come up with different answers. There should be a correct answer for this. So here we can create like an example function. If you give it an int, it tells you input was an integer. If you give it a string, it tells you the input was a string. All right. And so if we call it with those things, we get what we expect here. Julia has dispatched this invocation to that method, and it's dispatched that invocation to that method. Okay, so it's sort of pattern matching, I suppose. Another way of describing it. And you can sort of see the methods. It has this int64 method and this string method there. We could do it slightly differently. So these two are two concrete types. And like we saw here, right? Imagine that's integer now. So, right, integer. So they're two concrete types and they don't overlap. But if you could imagine having, another type of objects over here and another kind of abstract type, those two things could overlap. Or you could talk about a type and a subtype. And there's different ways these things could relate to each other. So let's take an example F2, a different flavor. So it's sort of, rather than integer and string, it's like integer and any. So it prints this is an integer, this is not an integer. So If you call it with this one, this is more specific. Integer is more specific type than any, which is to say the set of all values is a smaller set, right? That's what more specific means, okay? So both of them match, and this one's more specific, so it chooses that, and you get this as the input there. For this one matches, this one matches, this one does not match. When there's only one possible match left, you don't have to worry about which is more specific. It has to be that one. It's the only possibility. All right, and that's what dispatch is in Julia. So even if they overlap, you get the most specific, and that's the rule. And when we talk about multiple dispatch in Julia, this is where you put these two things together, where we have multiple arguments and different patterns. So like if X and Y are both integers, both inputs are integers. Or if they're both strings, both inputs are strings. Or if they have different types, they're different types. And you can call it with different things, and Julia will match that up. Now, this can get complicated because these types might be abstract types, and they might overlap with each other in interesting ways. And then there's like this whole Cartesian products of these sets for these different inputs, right? And Julia has to figure out which is the most specific. So here's a question. Do you think there's always an answer to that question? If you have an arbitrary of types and abstract types and unions and all these things, is there always going to be a most specific method? Yeah, I've got some yeses and some nos, okay? So this is interesting. So you can easily create a situation like this one, where we've got three types, and you have a method defined on the left two, and a method defined on the right two. If I call it with the leftmost, it's fine, it has to be that, it's only one matching. If I call it the rightmost, it has to be that. If I call it with this one, they're both good. And there's no sense that we can say that sort of abstract type is bigger or smaller than that abstract type. They're not contained within each other, right? So it's actually ambiguous what you mean. And the last thing you want your computer program is it running and doing something you can't predict, right? Your computer program should run in a way you've programmed it to be predictable. So Julia will actually stop at that point in time and give an ambiguity error. Okay, and the way you fix that is you create a third method, which is just defined on int, and then it's unambiguous. Okay, but if you can imagine you have two arguments and you've got all these different sets, it gets harder and harder. But on the other hand, if you do it well, you get rewarded with all this power, all this way you can get Julia to assemble your program as Lego bricks in this really interesting way. Let's take a 10-minute break. Let's take a 10-minute break and get back at 6:04 if you're online. Yeah, thank you. If you have any questions on the chat, just let me know. I'll keep looking. Okay, everyone, that's our 10-minute break up. Okay, let's go again. So the last hour I did spend probably explaining in quite a little bit of depth how like functions are working on the inside and stuff like that, how logic's working. We've still got a fair bit of syntax and stuff in Julia, so I'm gonna like power through. Just beware. A whole bunch of ways of writing things, doing different things in Julia, how to do errors, and a whole bunch of stuff. So this little component of this lecture is going to be like a laundry list of all sorts of different things I want to show you. Again, please stop and interrupt me because the purpose is you kind of learn. But I also do want to get onto the more interesting stuff at the end, if we can. So we've talked about functions. They can have one argument or two arguments. They could also have an arbitrary number of arguments. So with these three dots sort of mean, and all the remaining ones. So you could have some concrete ones and then the rest of them, right? Interesting fact about this also covers the case that there's 0 inputs. So 0 or more inputs. What it does is it hoovers them up, sticks them in a tuple, and then inside here, you have this inputs variable, and that's tuple, okay? And tuples are iterable, so you can put it in a for loop. And you could, for example, have this function that adds up an arbitrary number of things. So this function, if I go add all 1, 2, 3, 4, 5, then I get 15, which is like a triangular number. All right. Here's a cool way of using this and putting it together. So especially in the next unit with Paul Verbeek, we're going to talk about things like solving polynomials and stuff, at least in modular arithmetic. But in general, like we could have this polynomial generator. So this is putting together this weird closure thing we were talking about earlier and this Varug's thing. So we're going to create a function which returns a function which is a polynomial. And you get to here define all the different exponents of this polynomial here. So you have some a, which is a whole bunch of different coefficients of your polynomial. The order of the polynomial is at length -1 because the first one is the constant offset, right? And so we're going to create this polynomial, which is itself a function of x, and it's going to return the sum of all the different terms, okay? So 0 to n, so that's n is length -1, so there's actually length a things that we're doing here, and we're going to sum over all those things. This thing here is called a generator, or you put that in an array, you make a comprehension. It's a bit of syntax sugar as well for like creating with the square brackets, you create like an array. Without the square brackets, it's just like a bare, lazy iterable. And so this will let you add up these coefficients times x to the power I, okay? And we could make that more efficient by keeping x and multiplying it once each time or something. But basically, this is really cool. We can create a polynomial with constant offset 1, linear coefficients 3, and quadratic coefficient -10. And we can call that with different things, right? Oh, I was going to show you plots, but I actually better power on, otherwise we're going to. But basically, this is really cool. This is a really cool way of doing higher order programming, right? It's pretty powerful. What you can then do is you could like import the roots package, which helps you find the roots of functions. They don't have to be polynomials. So this roots package, it doesn't know anything about your function. It doesn't know that it's polynomial. It's just going to find roots, which is, if anyone needs reminding, that means find points where this function has an output of 0, okay? And it'll use like Newton's search or something for that. And it will return these, you know, -1/5 and +1/2 as the roots of this quadratic, okay? And it's done this numerically without knowing that it's a quadratic. And so this is really cool. So we can do this like higher order polynomial generation here. We can import this roots package, which has nothing to do with our weird function generator, and put them together and come up with an answer really quickly in a few lines of code, okay? So if you wanted to write that in a low-level language, you'd have to write all those things by hand. You couldn't just copy and paste other people's code. I mean, you could, but you'd have to like piece it together manually. Optional arguments, you can provide a default value for arguments. So for example, let's say we're looking at a probability distribution, which is like a Gaussian. You know, Gaussian might have a like a mean and a standard deviation, right? And so we could default to a mean of 0 and a standard deviation of 1 in this distribution, for example, right? That's pretty straightforward. Here, just notice there's a very, very, very subtle difference here. Can anyone spot the difference between this one and that one? The semicolon. Okay, so if you really look here, there's a semicolon here. Okay, so you got to watch for those. That means all the arguments after this are keyword arguments. When you provide them to the function, when you call the function, you need to give their name equals value. Okay, so and the syntax for all this is actually reminiscence of a named tuple or vice versa. But like here we can call it like that with sigma equals 2.5. Have you guys seen how to input something like sigma? I may as well remind you in case anyone's missed that. So like in Julia, you can use LaTeX completions, like I can go sigma, and then I can press the tab key and I get sigma, right? Just to remind you that. And that can just be a variable. We can make a super flexible function which takes an arbitrary number of arguments and keyword arguments. This sounds a bit crazy. I have done this before to forward it to other functions to like intercept something and forward it somewhere else. It does work. It's kind of cool. We call this first set of arguments positional arguments because they have a place, whereas the other ones are named or keyword arguments because they have a name. They don't have to be in any particular order. Destructuring is one of my favorite bits of modern programming languages. So here, when you create things, there's usually a syntax for creating things like arrays or tuples and different things on the right-hand side. So we can create a tuple like with the number 42 and the string ABC inside of it. But we can deconstruct the tuple by putting something that looks like a tuple on the left-hand side. And what this tells Julia is take the first element of that thing and bind it to the variable A, and take the second element of that thing and bind it to the variable B. Okay, so we've sort of deconstructed. For tuples, it doesn't really matter what I call these things. In Julia, yeah. So one thing that's really, you might actually see this actually used in Julia is this expression. So this is a nice way of replacing things. So if I go like x equals 1, y equals 2, a really common mistake to make is go x equals y, y equals x, like that. And what's that going to do? Does anyone know what that's going to do? It's going to set them both to be 2. So x and y become 2. So the problem is what you've done is in the first case, you've overwritten x with y. You've completely lost the original version of x. There's no way to get it back anymore. Okay. But you've just got 2 copies of y. In this way, you can kind of quote unquote atomically or all at once swap them without kind of having this intermediate step where you have to have some temporary variable or something to hold that. That's kind of cool. You can deconstruct name tuples or things. You can deconstruct things in a struct using the syntax we use for a name tuple, which starts with a semicolon, which is like the keyword arguments inside a function, like this. So now I have some complex number, which is a struct with the field read, a struct with a field im, right? They're the real and imaginary components, and I can fetch them out with this deconstruction. Okay. So that's a nice little shortcut that can be handy sometimes. That's really weird that didn't do the print lines. I don't know why that didn't happen. Bizarre. Okay, one thing you do is destructure arguments as they come in. Oh, yeah. You can kind of like nest these destructurings, and you can also do it when you define the function. So that whole thing I've highlighted is like one of the arguments of the function, and then I'm destructuring it on that line where I've defined it. Okay. If anyone's used modern JavaScript, people use this all the time. But yeah, you can do this in Julia. Function composition and piping. Okay, this is cool. So sometimes what you want to do is you want to start with some data and then do something to it, and then do something else to it, and then do something else to it. And this is a really common way of manipulating data sets. And we'll see that, I think, in unit 7, 6, 7, when I'm back. And this thing is the pipe operator. It's a lot like the pipe operator in Unix shell. It's sort of like take the output of the thing on the left and pipe it into the thing on the right. All right, and it's left associative, so you kind of like you pipe that into there, and then you pipe both of those into ACOS, right? Yeah. This is like a set of instructions, right? It's like start with this, put that in, put that in, put that in. So start with this, put it in there, put it in there, put the answer in there, and then put that answer in there. Here, we're doing function composition. So what that means is we're not like eagerly putting these values in. We're creating a recipe or a function which lets you use two functions one after another many times over. So you get to keep that function and use it again and again. Okay. So you can like construct these kind of data pipelines and then apply it again and again to data, which can be sometimes that's a more useful pattern. But you know, functions are a big thing in Julia, and in Julia you can compose functions, which is like the fundamental operation of functions, right? It's composing them. So yeah. So this is one of the coolest things. So this is some syntax that was originally sort of came from MATLAB, but got extended in Julia. So we got this dot thing. Have you guys seen this? Did Paul cover that? Yeah, it's pretty cool. So you can have a whole bunch of values. Let's say these ones. So let's just put this here. All right. So that's that. Now, what that means is start at 0, go every half. But I actually want to see that. Okay, let's have a look. What is that? We can use collect, which puts things in an array for you. Okay, it iterates through it and adds it to an array. Fine. Yeah, so that's the values we're putting as inputs. And then I can call cos on all of those values all at once with a dot. And so I can't just call cos on a vector. That doesn't make sense. I can call cos with like a number, right? Yeah. Another way of writing this, if you ever see it, you might map the cos function over x range, and it will do a very similar thing as the dot one, which is syntax sugar for something called broadcast. I think that'll still work. Broadcast, yeah. Now, the difference between mapping and broadcasting is that you can, I can go like x range, I can go like y range equals like x range, and I'm going to do this thing. Oh, sorry, this thing, which shall create this like covector or adjoint vector or dual vector or column row vector, or columns and rows. And then I can go like x like dot plus x range dot plus y range, right? And so broadcasting will expand that out in different dimensions for you. Okay. Map won't do that. If I did that with map, it would say, oh, error, they're different shapes. They don't make sense. But broadcast is like a more general version of map. The way I think of broadcast is it tries to put together the keys the best way it can. The indices, keys, whatever you want to call that. There's this cute little macro here called @dot. And all it does is it sticks dots everywhere a dot can be stuck. Okay. And then usually that's quite useful for computing kind of like vectorized expressions and stuff, which is nice. The other thing that's sort of nice to do, notice here, is the code that this generates is very efficient, right? It's a nice vectorized code. You might notice if you use Python, for example, that NumPy is a lot faster than just bare Python arrays because it's using vectorized stuff. Here, you could write whatever, like a NumPy kernel you like in Julia just with a few extra dots, and it'll go away, compile that as if someone had written like an extension to NumPy and written all that C code for you, so that that one thing you want to compute is as fast as possible. Julia will just do that for you automatically. Okay. More items from control flow. Okay, so we've seen a bit of if and else. I didn't really cover else if, but it's sort of like if there's multiple possibilities, you can stick some else ifs in there. And we've looked a bit for a while, but there's a few other nuances to look at. Okay, so first one is to realize that loops, for loops in particular, aren't special. Okay. In Julia, there's this function called iterate. Okay, so anything that's iterable will have a method defined for iterate. So let's look at that. Methods, iterate. We can see 256 methods for iterate. There's all sorts of things, dictionaries, ranges, you know, there'll be strings, there'll be all sorts of things you can iterate in here, which means they'll work when you stick it in a for loop. That's what iterable means, right? And that just relies that you define iterate method for it. And so it does this really weird transformation. I actually don't want to go into it, but all it does is it creates a while loop where it keeps calling iterate and checks whether it's finished or not. If it's finished, it breaks, which is what this means. Nothing means it's finished. And otherwise, if it's not nothing, it has to be this tuple of the thing you want, thing you're iterating, the stuff you want, and some internal state, and that's completely invisible. It really depends on the thing you're iterating. It might be the index of an array, or it might be some horrible internal thing of a hash map, which indicates something you don't even want to know about. You know, it could be anything. So what I guess the takeaway here is iteration is not special. It's really easy to create your own types that iterate. Or you can create your own type of arrays in Julia, which behave a bit different to the normal ones, or, you know, use less memory or something. Exceptions. So errors and exceptions in Julia, they're synonyms. So when I say error, when I say exception, I just mean the same thing. Doesn't really matter which word you use. There's this function called error. And when we call it, we say it throws an error exception. Okay. But you could use this function called throw, which throws a particular type of exception you like. So you can create your own classes of exceptions. And you know, in Julia, you can create your own types, you can create your own error types as well. Okay. But usually they're just subtypes of some exception type. So let's have an example. We're looking at an algorithm. Well, okay, here's one we can see at the terminal. If I go square root of 4, I'm going to get 2. But what's the square root of -4, right? Well, Julia has complex numbers, so surely we'll figure out what to do here, right? Wrong. It says I have an error, and it's called a domain error, so the input wasn't in the right domain. But what you can do is explicitly request it does complex maths for you, right? So it has a helpful message and everything. That's why they've defined their own special error for this thing. So let's say we're doing something like trying to invert a matrix. Do you remember your linear algebra from last year? I hope. You can do a determinant, invert a linear 2x2 matrix in your head. Probably not. That's on the quiz. No, just joking. But there are things like this is an algorithm to invert 2x2 matrices. So first we check, well, is the matrix actually 2x2? And this can, putting these guards in your code can be really useful because when a function's misused, it tells you, you fix it and you move on and you write more code. Working code. If you don't do things like this, you might end up with invisible errors, all right, later on. This step's you'll probably recognize as the determinant of that little matrix. If the determinant's 0 or approximately 0, we'll just say it's singular, right? And you can't invert a singular matrix. You get infinities and stuff. It's all badness. So like that square root function, this function will check that its outputs, that the input makes sense and it can produce the output you want, or it'll throw an error and your code will stop. Right? And that can be better than continuing programming something that's broken. Because maybe that'll take days, or maybe that broken answer will be sent to your users, or your, people who bought things off you, and you'll look like an idiot. Or you'll hand in your homework and you've got the wrong answer, and you'll feel like an idiot, or whatever. Okay. So, for example, if we call it with some random 3x3 matrix, it tells you a nice, pretty error message, right? If you give it one that's not invertible, so 1, 1, 1, 1 is singular. They're not linearly independent. So that one, it comes up with that error that's singular. But if I just pick some random thing, it can probably invert it. That's fine. Okay. So here I'm using this random module. Why is it not? It's really bizarre. Sometimes it's not printing the outputs. Oh, here we go. It's just assertion though. So it's just checking here that the inversion, the calculation multiplied by the input itself is nearly at the identity matrix. Okay. And we can check that lots of times. And what we can do here is use this thing called try and catch. Okay. So you can use error or throw to create an exception. And you might think, oh, well, if that's thrown, then your program's over, right? All Julia quits, the universe ends, everyone dies. But it's not like that, right? You can recover. And to do that, you use try and catch. So if any error is thrown inside the try block, the error is caught by the catch block and E is the error. And you can do things with it like print it to the screen. Okay, so for example, I run services, like meaning websites and things which sit online and you can call it. If something goes wrong, I don't want that web server to break, right? What I want it to do is to report an error, like maybe to my terminal, or maybe even send it to the user that was trying to use the web server, and then continue with other requests, right? So this is a really common pattern in software engineering when you're making reliable systems. Probably less important for just solving smaller mathematical problems, though, right? But it's good to see this try and catch stuff. Sort of make you think what you can do with the errors. And when you catch these errors and things, you can kind of like actually see where in the call stack this happens. So let's say I create F, G, H, and all these different things. And H is like a singular matrix. And I do all these transformations to it. They don't really change the fact that it's singular. And this thing is still, why does it say A? Maybe I should say mat. Not that it matters in this case. But basically, you can kind of see, we started at the REPL or whatever here. We called H, then we called G, then we called F, and then we called my 2x2 inverse function. And that's the function that threw an error on a particular line of code, right? And you can use this to look at your program and figure out where is the problem? Oh, there's a problem there. Well, how did we get there? And then you're like, oh, it came from there. And the problem's usually not here at the top. The problem's usually somewhere in the middle, right? Because this is throwing an error because something that called it gave it bad inputs, usually. Not always. Sometimes it's like, broken there. But often, just a debugging tip, when you see these, you have to like step through it and think, where is the program at? How did it get here? What are the values of these different layers of the stack? And then try and reason through why you got that error. Just for completeness here, there's another thing in try and catch called finally, which would mean no matter whether it succeeded or failed, you always do the finally block. Okay, That's useful when you have resources. So let's say you're trying to open a file, you have some file name. You want to open the file, and then here you go, try finally. So no matter whether the thing you're doing to the file breaks or succeeds, you still want to close the file afterwards, right? No matter what. And so that's what this pattern lets you do. And this is a kind of a way where we're using these higher order functions in Julia, where we pass in a function into open. And this is a really common thing to see with things with resources when using open, where you pass in what you want to do, the logic of that expressed as a function itself or a lambda or whatever. So here we're going to like read the first 128 bytes of a file. If that file doesn't exist, you get an error. If the file exists but has less than 128 bytes, it's going to throw an error when you try and read them. Okay. And so what will happen is it'll get to this line of code, try and read 128 bytes. That'll fail, and then it'll close the file for you there. Right? Julia has this really interesting syntax called do. I don't really want to dwell on it. But like I said, Julia has too many ways to define functions. And I swear to God, this is the last time I'm going to define one for you today. There's this thing called do. It's like function. It takes some arguments here, and there's a body. Okay. What it does, it constructs that function, and then it jams it before all the arguments into the thing you just called. Okay. And the reason I swear it was just invented purely for these kind of patterns where we have things like open. If you notice, I showed you the map function and the broadcast function, and there's filter and reduce and things. They're also useful there because the function is the first argument, and you can map over an array and then do things to each element. Right, and that's a really nice, elegant way to write the code. But again, don't feel like you have to use every trick in the book, right? Just write nice, easy to write code that's not too fancy. But you might see this and it'd be confusing if I didn't cover it. Cool. Variable scope. Before we move on to scoping rules, any questions? As I said, it was going to be a laundry list, and it was. Yeah.
What happens if you don't close?
What happens if you don't close the file? So it's not so bad, but let's say you're using Linux, right? The Linux kernel has to keep that file open for you for your program until your program exits. And if you have like I said, a web service, right? Let's say you keep opening files and not closing them. Tracking all those open files, even for the Linux kernel, it's going to take some memory and some computation, right? And so eventually, you're either going to make your computer slow or run out of RAM, or the Unix kernel is going to be like, no more files for you. You're cut off, to protect itself. Okay, so that's why that's important. In many other languages like C and C++, you have to like explicitly delete even the memory you allocate. So Julia has a memory allocation for you and deallocates it for you when you don't need it anymore, right? So Julia could have like a open file deallocator, and you can actually do that. There's these finalizers you can attach to things, so that things automatically close. But yeah, you might have something where it's really critical. You might want to close a transaction to a database. Even if there's an error, you want to tell the database to roll back rather than let that transaction hang. You know, there's lots of cases you need this. Yeah. Yeah.
Successful, does it open? Do you have the option to close it afterwards, or does it just open and close straight away?
So if you're using this syntax or this one, it will open it and close it. So after this line of code, it's closed again.
So the
Well, you've put this logic in. Oh well, yeah. Okay, so I've got read IO this, right? So what this will actually do, it'll calculate that expression and return that. So I could have data equals at the front of this line, and that would have given me the data. Yeah. Or maybe the body of this function mutates stuff, like puts the data in structures for you, and then everything's ready afterwards. But that's a great question. Okay. Okay. One thing that can be really confusing when you're learning your first programming language is just figuring out all this stuff about variables and the scoping rules of variables, right? So we're just going to cover them just in the interest of being precise. Julia these days behaves relatively sane, like Python or JavaScript. It's not going to have terribly surprising behavior here. But again, if it's your first programming language, this stuff's pretty damn confusing, I have to say. There's a first rule. There's actually two kind of scopes. So a scope is like the set of variables which you can see at the moment. It's the context. So there's a variable called x, there's a variable called y. There's a bunch of functions like plus and minus and print line that I have access to, and they're all in scope. Okay. Now when I write, x equals 0, what does it do? Okay. Well, if I'm just at the REPL, or I'm at the, the lowest level of indentation in a file or something, what this will do is create what's called a global variable. So there are global variables, and they can be const or not const. And then there are local variables inside functions, and those variables die once the functions, they're temporary. When you call the function, they exist. When the function's finished, they're all gone again. Okay. So if you've done a bit of programming, you know what the stack is and what the heap is. The variables kind of live on the stack, and when that function disappears, that stack frame's erased, or reused or whatever. Yeah. So that's fine. So what this will do here is it will actually create a new local variable. So the default in Julia is that inside a function, you're always creating local variables rather than modifying the global ones. If you want to modify the global ones, you can use this global keyword down here. But this code is 100% equivalent to writing it this way, local x equals 1. And that says introduce a new variable called x. Okay, and you can put local wherever you want inside functions. You can't do it at global scope, obviously. But inside functions, or inside functions, or inside loops, inside functions, inside if statements, inside whiles, inside try catches, you create assignments, create variables. And sometimes you're rebinding or editing variables that exist in outer scopes. And sometimes you're creating new ones for the purpose of doing something in this block. And I don't care about it later, right? And so you can use local to say, I just want this thing to be local here. I'm not talking about the x out there, which maybe there's not even an x out there, but there was. I'm not talking about it. I'm talking about my x, my new x. Done. So you can kind of see here, for example, we're actually kind of like mutating, or not rebinding, I shouldn't say mutating. We're changing the value bound to global x here in this case. So here's a question. So in other code blocks, such as if, while, and for, the default is to overwrite in the existing local variables if they exist. If they don't exist, you're creating new ones. Okay. So let's look at these two sets of code. What do they do? Anyone? What will kind of F1 return? Anyone know? 10? Does everyone agree or disagree? Okay. And what about F2? What do you think F2 will return? 0. Okay. So what's happening is inside this block, we're creating this new x equals to I. We're not touching this one. Okay. So in this one, we're setting x equals to 0, and then we're setting x equals to 1, and we're going around the loop again, setting x equals 2, going around the loop again, setting x equals to 3. A real program, you'd do some calculation here, right? This is just for examples. Maybe add them or something. But eventually you get to 10, you set x equals to 10, and then you stop the loop and you return x. And this one, you're basically doing nothing inside this loop. That's a no-op. You're defining a variable and then throwing it away and doing the loop again. Okay. What do you think this one's going to do? Oh, what the hell? That was meant to error. What? Not really. I think this is because I've already got an F. I'm not 100% sure about this. F 100,001. What does this do? Returns 2. Oh, I know why. Ah, right. This is why it was meant to, because we already have X defined. So it's actually grabbed X from the global state. So I'm going to go like make a new Julia one and prove to you that I'm not an idiot. If I call that, what it does is going to say, well, X isn't defined, right? Because it's defined, it's referring to X in the global scope because it's not in the local scope. Inside a for loop, this creates a new variable if it doesn't already exist in local scope. And by default, it's careful, it won't overwrite things in global scope unless you explicitly tell it to, because that could affect other parts of your programs in a surprising way. But to get around that, I can go local X, and that just defines, there's some variable X. I'm not telling you what the value is yet. That'll appear later, right? So there's some local variable X that exists in this block at that level of indentation, right? And then this one's like, oh, I know about X. I don't need to create a new one. I'll use the existing one, put it there. And then this returns 3. Yeah. So just to repeat myself, the reason this returns something is there was a global variable defined higher up in this lecture notes called X, and it was equal to 1 at that point. Occasionally, you might want to use the value which is being iterated, and there's this another keyword called outer, and that lets you like keep the value that's being iterated, right? So it's like rebind X to the thing being iterated, and this can be useful. I mean, that seems kind of dumb here. This can be useful when you're like going to break at some point, and you want to know, okay, what if I keep the thing that I'm iterating at the point of breaking? Maybe that's what I'm interested in, right? I'm doing a search for something. When I find it, I break, and then I have it. That kind of thing. Just more syntax, just to learn, okay? But I just want to offer some general advice with variables and scoping. Just 3 sort of golden rules, if you can remember them. Try and not use global variables, okay? When you're writing your little scripts and things, when I write a script, it's just create a function, put all the variables inside of it, and then call the function after. Now, there's 2 reasons. One is actually Julia can compile that function faster. So that's just an aside usually. It's usually plenty fast. But in reality, just dealing with all these variables, they're not staying around. They're all temporary, right? Which can be handy, can be less confusing. Use distinct names so you don't have to worry about, like when you write X equals 3, well, which X is it? Is it that X or this X? Then just use a different name. You know, names are cheap. And the other thing is, the longer a variable stays around, use a longer name, use something more descriptive, okay? Again, typing is cheap. If it's sort of in some inner loop and it's only 3 lines of code, you can call it I, that's fine. But like a global scope, you have a global variable put I, it's like, well, what the fuck is I? You know. So the goal is for your programs to be simple and easy to read. You know, code is read more often than it's written. So don't focus on writing as little code as possible. Try and write it so it's like as readable as possible and obvious as possible. And this is good for other people, but it's also good for you tomorrow after you've stayed up to 3 a.m. trying to finish your project. You know, the next morning you're like, what did I do here? It's like, just make it, name things, describe what you're trying to compute. Yeah, this is fine. We have talked about things that are mutable and immutable in Julia. So when we mutate things, we're talking about a value or an object that exists in memory, and we're taking the data in memory or whatever, and we're changing it. But value or object still exists. It's just the insides of it has become different. And that's called mutation. Modifying things, mutation. And some things in Julia are mutable and some things are not. Numbers, I think I mentioned last week, numbers are generally immutable. Doesn't make sense to change the number 2. 2 is always 2, right? 2 is not a container that contains data that might change over time. 2 is just a number. It's just it is what it is, right? And 3 is a number. But in an array might be something that over the life of your program, you add things to the array, you delete things from the array, and arrays are mutable, okay? So the number 7's not mutable, but the array containing the number 7 is mutable. Let's create some mutating function that takes an array and sets first element of that array to 0. So let's see what this does. We start with x equals an array with a 1 in it. Before the call, it looks like that. After the call, it looks like that. So this is the same x, right? We haven't changed the variable x. X is still x. It's the same object. It's just changed on the inside. There are different ways you can change, like arrays you can push and pop. So push is like put something on the end. Pop is like pop it off the end. So you can grow them and shrink them, right? There's a function called setIndex, which is like syntax sugar for this kind of thing. And there's getIndex, which is syntax sugar for just that indexing thing, right? So everything in Julia is syntax sugar. That's one of the takeaways from today. And by convention, these things tend to add an exclamation mark. There's nothing special about exclamation mark. You can put exclamation marks anywhere in any variable names. It's just by convention. It's a little note to the user to say, hey, the thing that's coming in here, it's probably going to change, right? So don't rely on it not changing because you'll be surprised. Now variables, let's go back to variables. When we have a function, if I say rebind z, so I have z here, we have some input z, and we rebind it to that. This doesn't have any effect whatsoever on the input here, x, right? We've taken whatever x is, and we've given it into a new variable z, which is like a reference to, or binding of reference to that object, right? Now we're saying, okay, z, forget about that thing you just had a reference to, now refer to this other new thing, right? That doesn't do anything at all to this reference down here, right? It has no effect on that. So, you know, basically when functions, the good thing about functions is they kind of hide all those manipulations of variables inside themselves, right? Those temporary variables. And the other nice thing about the equals operator in Julia is it always means, you know, you're rebinding this whole variable to some new object or value. So let's look at some cases where we might just see some code that's dealing with immutable stuff. So here we're kind of like just using the equals operator to rebind things. So A first refers to 10, then B refers to A, and then B refers to 20. What is A? Well, A is still 10, right? But now suppose A is an array with a 10 in it. B is now that same array. And then we modify B so that it contains 20, right? Well, B and A are pointing to the same thing. We've modified what was inside B, so we've actually modified what was inside A, right? And this is what mutability is. This is fundamentally what's going on, yeah? To get around that, we might want to copy the array. So B could be a copy of A. We can edit that copy, and then A hasn't changed. Sometimes copy is not enough because copy just copies the outer data structure. So if it's a double nested array and we copy it, what we're doing is we're copying the reference to that inner array. And then here, we're getting the reference to inner array, and then we're editing the first element of that inner array and setting it to 20. So with the shallow copy here, we've actually mutated A. So copy isn't like a perfectly safe operation. If you want to be perfectly safe, there's this thing called deep copy, and that will go through all your data structures and make sure in RAM they're a completely new copy, completely fresh. Whereas copy literally is like map with the identity function. It just copies that first level of data. We have 4 more minutes. If I can get through this, then we get a really good lecture next time. So I'm going to power through. So we saw the union abstract type, and we saw generic types, but the last one we haven't really spoken much about is the abstract type tree. I spoke about any. So there's this type any, which represents everything. But you can create these other types using the abstract type keyword that are subtypes of other types. So this is a type tree. So if I look at x is like a floating point number, float 64, right? And the supertype of float 64 is abstract float. And the supertype of that is real. The supertype of that is not any. And the supertype of number is any. Any itself is sort of recursive, right? Any is everything. So it doesn't really have a supertype, but rather than throw an error, its supertype is any, right? So this is a relationship. So 2.3 is a number. 2.3 is not a string, right? Or it's not an abstract string. 2.3 is a float 64. So and really when I say is a, that's the same as talking about the type of it being a subtype, right? Those two things are one infers the other. One implies the other. Sorry. So float 64 is a type of number, but string is not a type of number, a subtype of number. All right. So there are abstract types and concrete types. So you can sort of see here, this is like a little helper function which tells you whether it's concrete or abstract. We're going to talk about this again in half a second, but also complex itself is not concrete because it has a type parameter. It's not really a concrete type until that type parameter is given to you. Yeah. So here, I don't even want you to read this code, but here I'm creating a tree and pre-printing it to you. So we're using some functions in Julia to kind of figure out which types are concrete, which aren't. And we're using some reflection to figure out, show me the type and children types of certain thing. So let's start with number, right? What are the subtypes of number? Well, complex, dual, and real, apparently. I'll define out of the box. You can add more types of numbers. You could add quaternions or something as a user later on. And for real numbers, you can have abstract floats, abstract irrationals, integers. Apparently rational is not a type of abstract irrational. I haven't. Oh, irrational, sorry. Rational, irrational. These are things like pi. So you might say 4 pi, different constants. And then there's different types of integers, signed integers, unsigned integers, things like that. Okay. So this is like a tree, and it can be as deep as you want. Yes.
What is parameterized?
Parameterized. So like complex. So let's go back to where the font is bigger. So we could have like complex, right? And that's a type. And actually, I'm going to talk about this in a second. But so complex has a type parameter, which should be a real number, right? And that's the float 64 here.
Is that like vector?
And vector. We can have vector of string, right? And you can have vector of any, in fact, right? You can do all sorts of things like that. And that's the type parameter for vector. An array has 2, right? It has the dimensionality and the element type. Dum-de-dum. So we could create this type tree using this abstract type keyword. Okay, so it just looks like that. I just went through, I think, these parameterized or generic types. I'll just mention them quick. Complex itself is an abstract type, which sort of means it's like the union of all possible complex. Here we go. We've got to write it. We've got to write it here, right? Did I write it? Surely I wrote this down. But what it kind of means, here we go. Yeah, there it is. The abstract type, which is the union of all concrete types, complex T, for all possible T's, which are reals. Okay, so it's an abstract, that's a very abstract concept, right? It could be a union of infinite number of different types, right? There's no real limit to how many types you can define in Julia. But this is called a union all type internally in Julia. You don't really need to know that. But that's like, let's say, a union of infinite things. And we've already seen the union of a finite number of things, this union thing. And I'll just tell you two little facts about this. One is you can take the union of more than two things, like 3 or 4 things or whatever. Julia's smart enough, it knows identity like that, right? It can simplify things. It knows a lot of set theory, basically. And there's this type union with nothing at all, which the union of no types. So this represents the type where you can't make any values for it, okay? And so during type inference, remember the compiler will constantly try and figure out what the type of everything is. It can use this special type to say, oh, okay, now that thing can't possibly exist, right? There's no value, that can't possibly be value, so I'm going to call it this. And you know, and it's the opposite of any. Any is everything's any, and nothing is union. Top and bottom types in a hierarchy or a tree. It's like union is like the leaf at the bottom of the tree that has no values in it. And that's that. That means you've seen every concrete type in Julia and how to create them, every abstract type in Julia, what they mean, how multiple dispatch works, how to create functions, methods. Okay. So now we are ready. We're finally ready. So next Monday, we're going to go through and create some fun Julia programs. I'm going to update the notes here, so don't bother read ahead. I'll try and make something a bit more fun if I can. And yeah, that's it for today. Sorry I dragged on a few minutes extra, but we got where we wanted to get to. Thank you. Okay.